Okay, some revision, some definition for probability. I'll just quickly go through that and give you an example for that. So a trial is a single experiment, and it's like such as a toss of a coin, or like toss like a dice. That's an experiment. You can just say you do something. Okay, you do something and observe the result. You observe the outcomes. That's called a trial. So an outcome is the possible result from the experiment. So what is the outcome for tossing a coin? So it can be head or it can be tails. Okay, that's the two possible outcomes from that trial. Then we have a sample space. So sample space is the collection of the outcomes. So you just list out all the outcomes. Okay, so you list out all the outcomes and write that in a sample space. So for throw a dice, I can have 1, 2, 3, 4, 5, 6 as my sample space. So each of them is an outcome. Okay? Each of them is an outcome. So the collection will be a sample space. Okay, an event. An event is the list of the favorable outcomes. It is the subset of the sample space. Okay, it is the subset of the sample space. So what is the event? Event will be what I'm interested in. Okay, so what I want to see, what I want to observe. For example, I throw the dice and I want to see even number. Okay, then this event is 2, 4, and 6. Okay, this event will be 2, 4, and 6. 2, 4, and 6. 2, 4, 6 is the subset of the total sample space. Okay, so event will be what you're trying to observe, what you're trying to record it. So that's called an event. And then for any event, there will be a probability. So what's the probability of getting ahead? You know that's a half. Okay, what's the probability for tomorrow is raining? Maybe chance is 0.9. Okay, for Melbourne, maybe 0.9. What's the probability you can win the prize? Maybe it's 1 over a million. Okay, that's the probability. So each event will get a probability, but this probability will be like, we'll get some restrictions. First of all, that restriction must be, this probability is greater than 0. We never talk about negative probability. And also probability of that event needs to be less than 1 or equals to 1 as well. Okay, you either 100% sure that could happen, or you're not that sure it could happen or not. But it can't say 200% sure. Okay, in maths we don't have 200% sure or something. Okay, so the probability will be in between 0 and 1. And the sum of all the probability outcomes will be 1. So for tomorrow, whether it's rain or not, there's 2 outcomes. Okay, rain or not rain. You add up the probability for those 2, it must give you a 1. If the probability of raining is 0.3, then the probability of not raining is 0.7. They must add up to 1. Okay, the total probability must be equal to 1. And we have equal likely outcomes. So what are equal likely outcomes? So equal likely outcomes are the probability got the same chance of occurring for each outcome. Like tossing the coin, throw a dice. Okay, all the outcomes get the same probability. So for the coin, you have half and half. So throw the dice, you have 1/6 for each outcomes. Okay, 1/6 for each outcomes. So they are equal likely events. Okay, they are equal likely events. In the study of probability, a numerical value based on scale from 0 to 1 is used to describe the levels of chance. So we have 0 to 1 to describe chance. 0.5 is half of the chance. 0.8 will be very likely to happen. 1 is definitely happen. 0 is no way to happen. Okay, so that's the scale. The probability in which outcomes are equal likely will be calculated as the following. Okay, the number of outcomes in this event over the total number of outcomes, like in total. So for example, I want to get even number from the dice. Okay, I can have 2, 4, and 6. This is 3 outcomes. Okay, the number of outcomes is 3. So the sample space is all the outcomes. 1, 2, 3, 4, 5, 6, and 6. There's 6 outcomes here. So the probability of even numbers, getting even numbers, will be 3 on 6. That's just half. Okay, that's just half. That's what you learned last year. And we have two things. One is called theoretical probability. One is called experimental probability. Okay, how to think about this case? What's the theoretical probability you toss a coin and you want to get a hat? That is half. Okay, half chance. That's theoretical. But actually, you do this experiment. You toss the coin 600 times. You won't get exactly 300 times with hat, right? Like that's really like something really random. Like you just do, like say we do 600 times and we only get 250 with hats. Okay, the rest all tails, which is not exactly half. But this is called experimental probability. That is by experiment what you get the probability. So you use 250 over 600, get that probability, and that's the probability for getting hats. Okay, so not in theoretical, in the experiment what we get. For example, it's not necessary to be half. You believe it should be a half. But what you achieve in the end is like you use the coin for too long and it's just destroy some part and the probability changed. It's not a fair coin anymore. So you can get a greater chance to get a head or like a greater chance to get a tail. It's possible. Okay, it's possible. Or sometimes the design is not very good and it's not a fair coin. And then the probability change is not necessary to be half. So by the experiment, we can see it. But like if you only do the experiment for 10 times and you get 10 tails, can you just say the probability of getting head is 0? No, okay? You just do it like 2 little times, okay? If you do more, okay, so this is called the long run proportion. If you do more and more and more, like infinite many times, like the more is better, the more is better. So this is called the long run proportion. So 600 times is not good enough yet. We can do 6,000 times and to see what's the probability. It may not be exactly 3,000 as well, but it will get really close to 3,000 then. It will get 3,010, 3,005, like something like that. Okay, so it will get closer and closer and closer to a half if it's a fair coin. So in the long run proportion, the experimental probability will be approaching to theoretical probability. Okay, approaching. So the experimental probability is getting closer and closer to the theoretical one. Or maybe sometimes just exactly the same as the theoretical. So the more you do it, the better result you can get. Well, if I only do 2 times, you can just by luck, okay, I get both head or both tail, or very easy to get both head, both tail. But if I do a long run proportion, it can get rid of the lucky effect, and then we can see the true probability in the end. Okay, if we do like 1,000,000 of times, that will be enough. Okay, so let's just have a look at example 1. Example 1 says a card is drawn at random from a pack of 52 cards, and what is the probability that the card is not a heart? Okay, probability is not a heart. Okay, what is the probability it is a heart? Okay, so you have
30 out of
30 out of 52, it is a heart. Okay, that's a quarter. So not a heart will just be 1 minus a quarter. That's 3 quarters. Okay, 3 quarters. Have a think, in each type of the card, like ace, 2, 3, 4, each card you have 1 heart, right? 3 of them are not heart. So it's just a 3 out of 4 case for this one. Okay, what is not an ace? What's the probability of getting an ace? What's the probability of getting an ace? 1 on 13. Okay, you have 13 types of the card, and 4 ace, 4 on 52, 1 on 13. So it's just 1 minus 1 on 13. That gives you 12 on 13 will be the probability. Okay, they are equal likely events. You have the same chance of getting each different card. Okay, for any card, you have the same probability of getting it. Okay, so it's 1 on 52 of the probability to get each individual card. Then let's have a look at example 2. Okay, a random experiment may result in outcomes A, B, C, D, or E. A, B, C, D are equal likely, and E is twice as likely as A. So it is also twice as likely as anything. Okay, so it's same as how can I sketch for it? If I have that. Okay, I divide this area into 6. Okay, into 6. I have A, B, C, D. They have the same proportion, but E will occupy 2 space. Okay, they are equal likely. So E will be 2. Okay, it will be 2 of the area. So find the probability of E. So the probability of E equals to 2 on 6, which is a third. And the probability of B naught will be 1 minus the probability B, because in total it should give you 1. So 1 minus probability B is 1 minus 1 on 6. That gives you 5 on 6. Okay, that gives you 5 on 6. Okay, that is the probability. Okay, that's example 2. Let's have a look at example 3. Okay, let's have a look at example 3. Okay, for example 3, in order to investigate the probability that a drawing pin lands point up, Katya decides to toss it 50 times and count the number of favorable outcomes. So the favorable outcomes, okay, what they want to see is the pins lands up. Right, that's what they investigate. Okay, the pin lands up is the favorable outcomes, which turns out to be 33 times. Okay, 50 times, 33 times is pin lands up. And Mickey repeats the experiment, but tosses the same pin for 100 times. It's doing more trials. And 62 favorable outcomes appear. Okay, so what is Katya's estimate of the probability of the drawing pin landing point up? Okay, let's answer the first one. That probability will just be 33 over 50. That's 0.66. Okay, that is 0.66. Number 2 is asking, this is experimental probability. Okay, this is experimental probability. So number 2 is asking, what is Mickey's estimate? Okay, if it's Mickey's estimate, it's 62 over 100. That is 0.62. Okay, 0.62 by doing the experiment. Number 3, what I'm asking is, which of these is the favorable, preferred estimate to do this experiment? Which one is preferred? Which result? Well, if you choose one of the result, which one you choose? Second? Yeah, Mickey's. Okay, the second, because the more the better. Okay, the more you're doing is get approaching to this theoretical one. So you answer Mickey's. Okay, you answer Mickey's here. Okay, number 4 is an interesting question here. Okay, number 4 is an interesting question here. Number 4 says, based on all this information available, can you give an even preferred estimate for the probability? Okay. Well, I'm not going to take 0.62. I'm not going to take 0.66. What are you going to do?
0.64.
You mean averaging them?
Yeah.
Okay, that's what most of you think about. Is that correct? Averaging them? When you average something, they should have the same conditions. One just toast 50, and the other one just contributes 100 times. Do you think they can really do averaging? Yeah, very good. Thinking add what together? 33 and 62. So you will think about in total how many they're doing. Like at beginning, I was thinking about like averaging as well, but like then I realized it's not like half-half situation. Like it's not 100 times, 100 times situation. So I can't really do that. It's not going to give me the correct answer. So I would think the more the better. How I can create more events? How can I create more trials? 150 is the total number of trials we're doing together. And 33 and 62, which is a 95, will be the total number of pins length up. That just gives you divide by 5 is a 30, divide by 5 is a 9. Okay, it's a 19 over 30. It's a 19 over 30 in this case. All right. So that's about experimental probability. Okay, this whole question is about experimental probability. How do we do this? All right, that's the revision part. Let's have a think about next exercise. It's called the union and intersections. Okay, it's called the union and intersections. So a set is a collection or group of elements that including numbers, letters, or other objects. So a set, like we'll talk about set more in year 11, but what is a set? A set is a collection of things. Just like sample space, it's a collection of the outcomes. Okay, sample space is a collection of the outcomes. Well, I can say it's a collection of A, B, C, D, E, F, G, until Z. Okay, it's a collection of letters. Well, I can do a collection of all your names. Okay, 24 students in the classroom and a collection of all the names. So this is called a set. Set is just with a curly bracket. Okay, set is with a curly bracket and have all the elements inside. Okay, elements. So all the outcomes can be elements. Okay, it's part of the member of the set. Okay, I just give them a house like the curly bracket and put everything inside. Okay, that is called a set. Sample space is dominated by all of the symbols. Okay, all of the symbols. The common used one is the last one here. Okay, it's a really grid shape. Okay, I can never sketch for it. I think it's like a 3, somehow like that, but it's really ugly shape. So it's like a 3 in the other way. So this sign represents the sample space. Okay, every time you see that, it means that it's taking all the outcomes. Okay, it's all outcomes from like any trials. And objects, and this is called a universal set. Okay, sample space can also called a universal set. It means everything. Okay, it means everything in the set. It's all the possible outcomes. So it's called a universal set. Okay, next is called a Venn diagram. Okay, what is a Venn diagram? A Venn diagram is like normally a rectangle and some circles inside. I'm sure like this is a one circle, one events Venn diagram. There's a two events Venn diagram. I can also have like 3 circles, 3 events Venn diagram, as many as I want. Okay, as many as I want. Well, we will learn 3 Venn diagram this year. Okay, we will learn 3 Venn diagram this year. Actually, just talking about something fun. You may think about why you learn math and why we really learn Venn diagram. Actually, I play a game like recently, and that game is like you trying to read values from the Venn diagram. They give you some events, like if it's a blue one, that's circle 1. If that's a red one, it's circle 2. If it's with a star, it's circle 3. And if it's like with the light, it's circle 4. There's 4 circles in the Venn diagram. Okay, and they give you a lot of options there and say, if that's the intersection between the set, you will cut this line. If it's not, you're not going to cut. If it's that, you're going to the next one. So there's a lot of options there. Actually, I need to read the thing from the Venn diagram, and I find it so hard. Okay, it's actually so hard. And my partner just said, are you really a math teacher? A Venn diagram, you can't even read a Venn diagram. I said, it's a 4-circle Venn diagram. There's so many events here, I just can't do it. Sometimes I feel like really hard. And that game is really fun, actually. Because of the Venn diagram, I quite enjoy it. Okay, so you may meet some games in the future and they ask you to do the Venn diagram. If you have no knowledge about that, you just can't do it. Okay, so that's why you learn it. All right. So come back to the study. So we have 1 circle and 2 circle Venn diagram. They are easy. Just look at the 2 circle one. Just give the name to you. Okay. If it's the middle section, we say that's the probability A intersects B. Okay, not necessarily probability. It's just the set of A intersects B. It's the common area. Okay, it's the common area. And we have this part. This part. Okay, this is only B. This is called B only. So if we use a symbol that is A dash intersects B, I don't want A and I want B. Okay, it's A dash intersects B. If we're looking for this section here, this is called A only. Only have A, no B. We call this A intersects B dash. A intersects B dash. Okay, we want A but not B. And everything outside here, I have 2 ways to represent that. Whether it can be A dash intersects B dash. I want not A, not B. Okay, it's not belongs to A, not belongs to B. A dash, B dash, not. Intersections. Or it can be A union B. Whole thing dash. So what is A union B? A union B is this thing. That is A union B. Okay, that is A union B. Everything. Okay, either A or B or both. Okay, that's called A union B. So everything dash is not that set, which will give you the complementary one. Okay, we'll give you the complementary one. All right, so that's the notations for each individual pass. You may need to know this later. I just give you the notation here first. All right, and we have a non or empty set. Okay, what is a non or like this is the name? A non-set or empty set. It's a set with no elements. Okay, is like no elements. Okay, we can use 2 symbols. This is one symbol. This is one symbol. We normally use the back one. Okay, that is like really visual. Okay, in a set there's nothing. There's no element in the set. You can use that to represent as an empty set, but like no one really used for it. Okay, we all use this one. It looks nice. Okay, it looks better. So it's called empty set. Okay, empty set. Nothing in the set. So, okay, we have the intersection and union. Okay, intersection and union. So you know what is intersection? Intersection is both belongs to A and belongs to B. Okay, A and B. It must be the small part in the middle. If it's union, is either in A or in B make up the union. So if it's in A, satisfied. If it's in B, yes, satisfied. It will be the whole thing of the two circles. Okay, the whole thing of the two circles. So that is the union set, either in A or in B. So that's the intersection and the union. And then we have mutually exclusive. So what is mutually exclusive? Mutually exclusive means there's no elements in common for two events, which is the representation will be A intersects B equals to empty set. If I use a Venn diagram to represent that, that will be it. Okay, no intersections, they're not touching each other, there's no common areas. This is A intersects B equals to empty set. These two events are called mutually exclusive events. Okay, mutually exclusive events. When you talk about mutually exclusive, there's no elements in common. And we have something called complementary events. Okay, complementary events. So as I mentioned before as well, complementary is just A dash equals to 1 minus probability A. So you want the whole area to be 1. So if you have this part already, what's the rest? What's the rest? So if in a Venn diagram, that is A. That is A. Okay, that is A. All the rest will be A dash. They in total make a 1 for you, but they not overlap. Okay, they're not overlapping each other. They make a 1 for you, but there's no intersections between them. A and A dash will be mutually exclusive events. Okay, will be mutually exclusive events. They in total make up a 1, but there's no intersections. Alright. And we have the next one, is called A only. I have explained what is A only. It's only in the set A, but not touching with B. Okay, the common set has been excluded. I just want A. So the notation will be A intersects B dash. Okay, A intersects not B. I don't want B, I just want A. And then we have, okay, most important thing is this one. Because it's not really something hard, it's just like you keep forgetting. I just keep testing this area every year, year 9, year 10, and just everyone forget it. So N means the number. It's nothing to do with the probability. It's nothing to do with the actual outcome. It's nothing to do with the like what number inside your set. It's just how many are there in your set. Okay, how many outcomes are there? N means the number of outcomes in A. Let's do an example. If A equals to that. Okay, that's the set A. That is the set A. What is the number of set A? That is 5. Okay? 5 is not the element for set A. But it's how many? Okay, 1, 4, 7, 9, and 11. Okay, there are 5. Okay, there are 5. So NA equals to 5 is asking how many elements are there in that set A. Okay, must remember that. I don't want to see any mistakes in the exam or test. There will be some question like that. Okay, so number of the elements in one set. So N means the number of elements. All right. Next one. Next one is called a probability table. We call it a probability table, or we also call it is a Carnot map. Okay, a Carnot map. So what's this table doing? Like what is good thing for this table? Well, it's only used when there's 2 events. Okay, only working when there's 2 events. If there's more events, it's not going to work. I have events A, I have events B. Okay, A dash, B dash. So this gives you the total number of B. This gives you the total number of B naught. That is the total number of people in this event. So each box, each 4 box in the middle, that gives you the intersections. Okay, A intersects B, A intersects B dash, A dash intersects B, A dash intersects B dash. So the good thing is, if you add them horizontally, it gives you the last value. If you add them vertically, that will give you the below value as well. Okay, you can add this way. You can add this way. So if you add them, they give you the same number. So if you know about 3 or 4 values in this table, you can know all the rest. Okay, you can know all the rest. That's the best thing I love in probability. Okay, I like this table. So it can use for numbers. Okay, it can use for numbers. Okay, number, how many other. It can also use for probabilities. Okay, it can also use for probabilities. Then the total here must be 1. Because the probability for total is 1. Okay, you're adding them. You're adding A dash. That must give you a 1. So you have 1 here. Alright. Let's just have a look at examples below here. Okay, let's just have a look at examples below here. We have example 1. Okay, example 1. 1, 2, 3, 4, 5, 6. There are the outcomes are equal likely. If A is 2, 4, 6 and B is 3, find the probability for A union B. So first of all, let's have a look. What is A union B? A union B is 2, 3, 4, 6. That's the union. 2, 3, 4, 6. That's the union. So probability of A union B is the number of A union B over the number of total. Number of A union B, there are 4 elements there. Total is 6 elements there. It's 4 and 6, which is a 2/3. Okay. How many other? Because they are equal likely. First of all, the word equal likely are very important. Without equal likely, you can't do it by this way. Okay, you can't do it by this way. There's different ways you will do. So like in year 11, you will learn different ways of doing that. But now I only am doing 2/3 here. For intersections, okay, what is the intersection here? What's A intersects B? It's not 0. Nothing. Okay, it's empty set. It's the non-set. So that equals to this. The number of elements in that set is a 0. Okay, the number of elements in that set is a 0. This means that A and B are mutually exclusive events. Okay, A and B are mutually exclusive events. Okay. A and B are mutually exclusive events. So B will just be probability A intersects B is a 0 because the numerator is a 0. Okay, numerator is a 0. Number of A intersects B is a 0. Then the total is a 0. Okay, a total is a 0. Probability of A dash. Okay, probability of A dash is 1 minus probability A. As I explained before, it's 1 minus probability A. So what is 1 minus probability A? Is 1 minus half. That is half. Okay, how I can say that's half? That's a 3 on 6. Number of elements in A over the elements total. So 3 on 6. That gives me a half. B, probability B dash is 1 minus probability B. That is 1 minus 1 on 6. That is 5 on 6. Okay, probability A dash always equals to 1 minus probability A. It always equals to 1 minus probability A. Alright, I want you to do example 2 and example 3. This one is using a Venn diagram, this using a Carnot map. Okay, for number 2 and number 3. Have a try of those two questions. Try to set up the table and the Venn diagram, and we'll compare the answer together at the beginning of next lesson. Okay.